Hello everyone, my name is Khaled Harmoush and I'm presenting our work titled Efficient Intrusion Detection in Computer Networks using Feature-Optimized Machine Learning, conducted in collaboration with Dr. Quoc-Nam Tran at Southeastern Louisiana University. In this work, we focus on improving the accuracy and efficiency of intrusion detection systems using machine learning and feature optimization techniques. In this presentation, I'll begin with the motivation and problem statement, followed by the importance of intrusion detection systems. I will then discuss the limitations of traditional approaches, introduce our proposed methodology, and describe the dataset and feature engineering process. Finally, I'll present our experimental results, key findings, and conclude with future work. Cyber attacks are rapidly increasing in both scale and sophistication, posing significant risks to modern computing infrastructures. Traditional intrusion detection systems often struggle to handle large-scale, high-dimensional network data efficiently. This creates a strong need for solutions that are not only accurate, but also scalable and computationally efficient. Why IDS matters. Intrusion detection systems play a critical role in maintaining the confidentiality, integrity, and availability of systems, commonly known as the CIA triad. They prevent unauthorized access, protect data from tampering, and ensure continuous system availability. This is especially important in modern environments, such as cloud systems, IoT networks, and large-scale distributed infrastructures, where the attack surface is significantly larger. IDS systems continuously monitor network activity to detect indicators of compromise, such as abnormal traffic patterns, unauthorized access attempts, and malicious behavior, like DDoS attacks. IDS limitations. Traditional intrusion detection systems rely on two main approaches: signature-based and anomaly-based detection. Signature-based systems are limited to known attack patterns and cannot detect new or zero-day threats. They also require continuous updates. On the other hand, anomaly-based systems can detect deviations from normal behavior, but they often suffer from high false positive rates and difficulty distinguishing between legitimate and malicious activity. These limitations highlight the need for more adaptive and intelligent detection methods. Framework and methodology. Our approach follows the structured pipeline, as you can see. We begin with the CIC IDS 2017 dataset, followed by the pre-processing steps such as data cleaning, normalization, and balancing. Next, we apply feature engineering techniques, including extraction, transformation, and selection. We then train multiple machine learning models, and finally evaluate their performance based on accuracy, reliability, and efficiency. Dataset overview. We use the CIC IDS 2017 dataset, which is a widely recognized benchmark for intrusion detection research. It includes both normal and malicious traffic, with a wide range of modern attack types. The dataset contains approximately 83 network flow features, including IP addresses, ports, packet sizes, and time-based attributes. Its realism and diversity makes it well-suited for evaluating IDS performance. Dataset characteristics. The dataset consists of approximately 2.8 million network records, collected over 5 days of real-world traffic. It includes 15 traffic classes, including benign traffic, and multiple types of attacks, such as denial of service, brute force, and web-based attacks. However, it also presents challenges, including class imbalance and high dimensionality, which must be addressed for effective model performance. Data preprocessing. Data preprocessing is a critical step in our methodology, as the quality of the input data directly impacts the performance of the machine learning models. We begin with data cleaning, where we remove missing and infinite values that may result from errors during data collection. These values can negatively affect model training and lead to unreliable predictions. We also eliminate duplicate records to prevent bias, as repeated data points can distort the learning process and cause the model to overfit certain patterns. Next, we perform data normalization using z-score scaling. This standardizes the range of all features so that they may have a mean of 0 and a standard deviation of 1. This step is especially important because the dataset contains features with different scales, such as packet sizes and time intervals. Without normalization, features with larger numerical values could dominate the learning process. We can address class imbalance, which is a common challenge in intrusion detection datasets. Some attack types are significantly underrepresented compared to normal traffic. To mitigate this, we apply balancing techniques to ensure that the models can learn effectively from both normal and malicious traffic, improving their ability to generalize to unseen data. Overall, preprocessing helps reduce noise, eliminate bias, and prepare the dataset for effective feature engineering and model training. Without proper preprocessing, even the most advanced machine learning models would struggle to achieve reliable performance. Feature engineering. Feature engineering represents the core contribution of this work and plays a critical role in improving both the efficiency and effectiveness of the intrusion detection system. We begin with feature extraction, where we derive meaningful attributes from raw network traffic data. These attributes capture important characteristics such as packet behavior, communication patterns, and protocol-level information. Next, we perform feature transformation, which includes normalizing and standardizing the data. This ensures that all features are on a consistent scale and improves the learning process of the machine learning models. The most important step in this pipeline is feature selection, where we identify and retain only the most informative features, removing redundant or irrelevant ones. Intrusion detection datasets are typically high-dimensional, meaning they contain many features that may not contribute significantly to classification performance. By applying feature selection techniques, we are able to reduce this complexity while preserving the most critical information needed for accurate detection. As a result of this process, we achieve approximately an 80% reduction in the feature space, with only minimal impact on detection accuracy. This is a significant improvement because it reduces computational cost, speeds up both training and inference, and enhances the scalability of the system. Overall, feature engineering allows us to transform raw data into an optimized representation that enables efficient and accurate intrusion detection. Machine learning models. In this study, we evaluate several machine learning models to classify network traffic. First, decision trees operate like a flowchart, where decisions are made through a sequence of rule-based splits. This makes them highly interpretable and easy to understand. Random forest extends this idea by combining multiple decision trees, as we can see. Each tree makes a prediction, and the final classification is determined by majority voting, which improves accuracy and reduces overfitting. Support vector machines take a different approach by finding an optimal boundary, or hyperplane, that maximizes the separation between normal and malicious traffic. This makes them particularly effective in high-dimensional datasets. Finally, k-nearest neighbors is a distance-based method that classifies data based on the closest data points in the feature space. It is simple and intuitive, relying on similarity between observations. Together, these models provide a comprehensive evaluation of different classification strategies for intrusion detection. Valuation metrics. We evaluate our models using several key metrics. Accuracy measures overall correctness, while false positives and false negatives assess detection reliability. Robustness evaluates how well the models perform across different attack types, including unseen threats. Efficiency measures computational time and resource usage, which is critical for real-time systems. Our goal is to balance high accuracy with low computational cost. Results. In our experiments, we use Quoc-Nam as the primary tool for model exploration and feature optimization. Quoc-Nam allows us to systematically evaluate feature subsets by recursively reducing the number of attributes, from the original 83 features down to 60, 50, 25, and ultimately 15 features. Today we're going to visualize the 83 versus the 15 features. At each stage, we analyze feature importance and remove redundant or less informative attributes, enabling us to understand how dimensionality impacts model performance. Once the optimized feature sets are obtained, we use scikit-learn to validate the results across multiple machine learning models. The results show high classification accuracy across all models, with strong detection of both known and previously unseen attacks, and low false positive and false negative rates. If we visualize these results, we observe that reducing the feature set significantly has only a minimal impact on accuracy. However, this reduction leads to substantial improvement in computational efficiency. Additionally, performance remains consistent across different classifiers and feature subsets, demonstrating the robustness of our approach. Therefore, we reduce from 83 features to just 15, with almost no loss in accuracy. This shows that many features in IDS datasets are redundant and can be safely removed without sacrificing performance. Key findings. Our key finding is that we achieved approximately an 80% reduction in feature dimensionality while maintaining nearly the same level of detection accuracy. This is a highly significant result because it indicates that a large portion of the original features in intrusion detection datasets are either redundant or contribute very little to the overall classification performance. In other words, the system does not need the full set of features to make accurate predictions. By eliminating these unnecessary features, we are able to significantly reduce the complexity of the dataset. This directly translates into improved computational efficiency. In our experiments, we observed performance improvements ranging from 10 to 100 times faster processing when compared to using the full feature set. This improvement impacts both training time and inference time, which is critical for real-time intrusion detection systems. Additionally, reducing the feature space helps mitigate issues related to high dimensionality, such as overfitting and increased computational cost. It also improves the scalability of the system, making it more suitable for large-scale and high-speed network environments. Another important observation is that the performance remains consistent across different machine learning models and feature subsets. This demonstrates that the feature optimization approach is robust and not dependent on a specific classifier. Overall, these results highlight the importance of efficiency feature selection in modern intrusion detection systems. They show that it is possible to achieve high accuracy while significantly improving efficiency, which is essential for practical deployment in real-world cybersecurity applications. System performance and deployment. Beyond accuracy and efficiency, it is important to evaluate how the system performs in real-world environments. Our approach enables real-time intrusion detection, meaning it can continuously monitor network traffic and identify potential threats as they occur. In terms of performance, the system is capable of handling network traffic speeds of up to 1 gigabit per second, which aligns with modern enterprise network requirements. Another key advantage is deployment flexibility. The system can be implemented on a single machine for smaller environments, or scaled across distributed systems and clusters for larger, high-demand infrastructures. This flexibility makes it adaptable to a wide range of use cases, from local networks to cloud-based systems. Additionally, the system demonstrates high scalability and low latency detection, which are critical for minimizing response time during cyber attacks. Overall, these characteristics make the proposed approach not only efficient in theory, but also practical and deployable in real-world cybersecurity environments. To conclude, this work demonstrates the machine learning techniques combined with effective feature optimization can significantly enhance the performance of intrusion detection systems. By reducing the feature dimensionality while maintaining high accuracy, we are able to improve both computational efficiency and scalability. This makes the system more suitable for real-time detection in modern, high-speed network environments. In terms of future work, we plan to extend this approach by integrating more advanced AI techniques, such as deep learning, to further improve the detection of complex and zero-day attacks. We also aim to evaluate the system in real-world deployment scenarios to better understand its performance under live network conditions. Additionally, integrating the system into cloud and edge environments will allow for more scalable and distributed intrusion detection. Finally, we plan to enhance the system's robustness against adversarial and evasive attacks, which remain key challenges in cybersecurity. Overall, this work highlights the importance of efficient data representation and intelligent modeling in building next-generation intrusion detection systems. Thank you for your time and attention.